Hello, everyone. In this section, we get to talk about how we can use Taylor series to do a lot of cool stuff and to make our calculations from stuff that was hard and tedious a whole lot easier. And to first start off, we're going to talk about limits. So back in when y'all took 1060, y'all had to do those nasty integral techniques and all of that. Or if it was indeterminate form of type 0 over 0 or infinity over infinity, we're out to do L'Hopital's rule and tackle it that way. Well, now we can, since we now know Taylor series, if my function I'm taking a limit, if I contain another function in which I already know the Taylor series around the center A, or where that limit is approaching, then I can say I can replace that g of s with its Taylor series around that point and check what that happens. One remark that I do want to make about this technicality is, let's say the limit was approaching infinity. If it was approaching infinity, then I don't really have anything to replace a Taylor series centered at infinity. That's something we never talked about. So if you have a limit going to infinity and you want to try to tackle that, then what we do for that is we replace the limit as x goes to infinity of f of x, and we call it t, where t equals 1 over x, which is why we have under the limit as t goes to 0 from the right, because if x was going to blow up to infinity, same thing as t going to 0 from the right. And that's also why instead of x, we have the 1 over t in red. And then with this new function of f evaluated 1 over t, we could do our technique that we talked about above in the highlighted area. But let's go ahead and see how we can use it for a typical limit. And let's try to evaluate this limit, e to the x minus 1 minus x over x squared, as x is going to 0. So I'll copy it back down here, limit, as x goes to 0 of e to the x minus 1 minus x over x squared. Now, if we were talking about tools from 1060, then the way we would have done this in Cal 1 was to note that this is an indeterminate form of type 0 over 0, and then we would evaluate the limit in that respect. Well, now let's say I want to use Taylor series instead. And how do I go about that? Well, in this example, a is going to 0. So what that means is, out of the functions that I see here, which function in f of x, where in this case f of x is the entire function e to the x minus 1 minus x divided by x squared, which function contained within f of x has, since I'm doing the limit acting as the center of the Taylor series, and since the center is 0, which one of these has a known Maclaurin series? And the answer to that, out of this, is e to the x, because we talked about in the previous section that the Maclaurin series for e to the x is the sum going from 0 to infinity of x to the k over k factorial. And so because I know that now, then within the limit as s goes to 0 of e to the x minus 1 minus x divided by x squared, I'm going to replace e to the x with this Maclaurin series. Since it's going to be nasty having that whole thing in the numerator with an x squared, what I'm going to do first, for presentation purposes, is I'm going to rewrite my function f of s as 1 over s squared times e to the x minus 1 minus x. And you don't have to do that. I'm doing that solely for presentation purposes. But so if you want to leave all that in the numerator, go for it. Now, since I know the Maclaurin series for e to the x, what I'm going to do is I am now going to replace e to the x with this known Maclaurin series. Okay, factorial, with it still being subtracted by 1 and by x. You might ask yourself, now why do I care about writing down the Maclaurin series? Well, the main benefit of writing down the Maclaurin series is that I could simplify my problem to be a whole lot easier to work with. And to make it more clear what I mean, let's expand out the terms of the Maclaurin series of e to the x to see what's happening here. If I explicitly wrote out the terms inside the Maclaurin series, k equals 0, I'll have x to the 0 power over 0 factorial, so I'll get 1. And k equals 1, plug in 1 for k, I'll get x. Plug in 2 for k, I'll get x squared over 2 factorial. Plug in 3, I will get x cubed over 3 factorial, and so on. And then I still have a minus 1 and a minus x within there. And now it's more clear how I can simplify after expanding the Maclaurin series. Because, have that scroll up on me. Because I have 1 minus 1, so those 1's get to go away. I have an x minus x, so the x's get to go away. Which means this now simplifies to become the limit as x goes to 0, 1 over x squared, and inside the parentheses I still have the x squared over 2 plus the x squared over 3 factorial, x cubed, not x squared, the x fourth over 4 factorial, and so on. Now my next step is I'm going to distribute that 1 over x squared to every term inside the parentheses. And when I do that, I get the limit as x goes to 0 of x squared in the numerator 2 times another x squared in the denominator plus x cubed over 3 factorial times x squared plus x to the 4th divided by 4 factorial times x squared, and so on. It's quick to check that for the first term, the x squares get to cancel out. For the second term, I simplified that down to just have x in the numerator. Simplified that down to just have x squared in the numerator. And essentially for every term thereafter, we are essentially going to continue on and subtract by 2 from the power, which means I now have the limit as x goes to 0 of 1/2 plus x over 3 factorial plus x squared over 4 factorial plus x cubed over 5 factorial, and so on. And now because I'm taking the limit as x goes to 0, and this is a polynomial, polynomials are continuous, so the limit of a continuous function is the exact same thing as plugging it in. So that's going to 0, that's going to 0, that's going to 0. Everything is going to 0 except for that first term, meaning that my limit equals 1/2 for that answer. Keep in mind that this will be the same answer that we will get if we do L'Hopital's rule for that. And so a fun exercise to do is try to take that limit of L'Hopital's rule and verify that you still get 1/2 as your answer. All right. Now another cool thing we can do with Taylor series is because Taylor series and Maclaurin series are just a very special form of a power series, then that means, just like with power series, we can differentiate and integrate a Taylor series term by term. And so for that, let's go ahead and take the derivative of negative the natural log of 1 minus x. So before we do that, let's go ahead and take the derivative of that function above to just note what we're trying to shoot for. Now take a derivative, have a constant of negative 1. So that'll be a negative natural log of 1 minus x. And derivative of natural log of 1 minus x is negative 1 over 1 minus x, which means I should expect the derivative of that to be 1 over 1 minus x. Now keep in mind that we talked about before that this has a Maclaurin series of the following form. So that means when we do the derivative term by term, I want that series to pop up to verify that. So let's go ahead and take the derivative again. The only difference this time is we're now going to do it term by term. All right, take derivative. And our derivative for negative natural log of 1 minus x is the sum going from k equals 0 to infinity of x to the k over k. Oh, that should be k equals 1. There we go. And talking about our property of derivatives for power series, a derivative of a power series tells me I can move the derivative inside the series and take the derivative step by step. And now this just becomes power rule, and so we have sum from k equals 1 to infinity of 1 over k times k x to the k minus 1. And because I have a 1 over k and a k, they cancel out, leaving me with sum from k goes from 1 to infinity of x to the k minus 1. And that is very similar to my power series above. The only differences are the exponent and where I started off my series. But I claim that these two series are the same. And here's why. If a series is very close to what you're trying to go for and is only off by maybe a -1 or a +1, then a useful technique to do is a change of variables. And what I do with a change of variables is I'm going to change something within my series, and with that change, I include a brand new variable that's going to become my new index for the series. So for this case, I see k minus 1, and so my logic is I'm going to set m to be k minus 1. And so that means wherever I see the old index k, I am going to change it with respect to m. And so let's change that series with respect to m now. Well, first thing to note, since I define m to be k minus 1, that's now k equals m. And now my series is going to start at 0 because of my original series, I started off at 1. So if I plug k equals 1 into my formula m, I'll have that m equals 0, which explains why my new series starts at 0 instead of starting at 1. And now we have the exact same power series as 1 over 1 minus x, which fits with what we talked about above as we expect for its derivative to occur. And now let's do this guy. We're going to verify, that's a typo, that we're going to integrate this Maclaurin series to verify that the antiderivative for cosine better be sine. Well, since that is a power series, we're going to integrate the Maclaurin series of cosine of x dx. And recall from the last section that that is defined as the sum from k equals 0 to infinity of negative 1 to the kth power, x to the 2k power over 2k factorial, and then you have a dx at the end for the variable. Since that is just a power series, I can move the integral inside the series to take the sum of the integral of negative 1 to the kth power, x to the 2k power divided by 2k factorial dx. And so negative 1 to the k and 2 to the 2k factorial, those are constants with respect to x, which means I'm only taking the integral of s to the 2k, which when I do that, I get that equal to the sum from k starting at 0 to infinity of negative 1 to the kth power plus, or times, x to the 2k plus 1 divided by a 2k plus 1 times the 2k factorial, and then there's a plus c on the side. Now, one thing I want to note, there we go, my apologies. One thing to note is 2k plus 1 times 2k factorial. That whole expression can be rewritten as 2k plus 1 factorial. Therefore, I can rewrite the series as the sum k equals 0 to infinity of negative 1 to the kth power, x to the 2k plus 1 over 2k plus 1 factorial plus c. And now we recognize that the series that I now have is the Maclaurin series for sine plus c. And there is my final answer for that problem. Now, Another application for a Taylor series is with differential equations. And you'll learn more about differential equations when you take Math 2080. But essentially what a differential equation is in a nutshell is I formed a system of equations where I have derivatives in them. So one basic example of a differential equation is I could say, oh, well, the first derivative of y has to equal y squared. Something like that, and then I'll have to use that to figure out what I need to do to solve for it. But we can actually start using Taylor series now and gather insights into solving a differential equation. And that's what's going to happen with example 4. Is we're going to find a solution for this differential equation where the first derivative equals f of x plus 2, where f of 0 equals 6. Now, some quick lingo for when y'all take 2080. Yes, I gave you an information about the original function f. Which means, I guess it's called an initial condition. I gave you information about the original function. That at 0, my output for f should be at 6. And let's see how we can use differential equations for that. The main strategy that I'm thinking of for yes, it's just like how we originally found out Taylor series, is we're going to take a lot of derivatives. The reason why I say we're going to take a lot of derivatives is because there we can find the coefficients that occur within our Taylor series. And so let's do that. So first we take the first derivative of f of x, which we already know by the given equation, that is equal to just f of x plus 2. And now let's go ahead and talk about the second derivative while we're at it. Oh, scroll back up, please. Thank you. So, second derivative, the way that we discuss the second derivative is that it's just a derivative of the first derivative, but based on my equation above, my first derivative is f of x plus 2. Now 2 is a constant, so that's going to go away. But f is a function that I can take as many derivatives as I want. So I just get back to f prime of x, which we know equals to f of x plus 2. Well, out of curiosity, let's take the third derivative and see what happens. Well, I claim the same thing is going to occur because I'm taking the derivative of the second derivative, which we already found to be f of x plus 2, because we showed before that the second derivative is just the first derivative, which means I'm back to f prime of x, which means I'm back to the f of x plus 2. And I say that's going to happen no matter what you're working with. So now let's start figuring out what we want to plug it in with, or what we want to center our Taylor series. Because I'm given initial information when I plug in 0, I'm going to let that initial information be my center for the Taylor series. So I'm essentially going to do a Maclaurin series. I plug in 0. Well, at f of 0, I know what information I'm given. I get sits. So at f0, I get sits. The first derivative, plug in 0. Since it's f of x plus 2, and f of 0 equals sits, as 6 plus 2 equals 8. And since all the other derivatives are equal to the first derivative, so that means the second and third derivative equal 8, and it means everything else should also equal 8. Alright, and now let's use this information to write down the Maclaurin series for f of x. Alright, so Maclaurin series tells me that I'm doing f at 0 and plus its first derivative at 0 over 1 factorial times x plus the second derivative at 0 over 2 factorial times x squared plus the third derivative at 0 over 3 factorial over x cubed, and so on. And plugging in our information, I have 6 plus 8x plus 8 divided by 2 factorial x squared plus 8 over 3 factorial x cubed, so on and so forth. Now, one tempting thing is to note that they all have 8s in them, and to factor in 8 and find this here and do it that way. However, I would be cautious because once I factor in 8 out, I have 8 x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 and so on. And so I am very close to the Maclaurin series for e to the x. So I'll make that as a note. I am very close to the Maclaurin series for e to the x. The only thing that I am missing is I'm missing a 1 to correspond to when I plug in 0. And if I'm missing something in this differential equation, I'm going to look at what I have left behind and I ask myself, how can I rewrite it such that a 1 can appear inside this parentheses? Well, for a 1 to appear in that parentheses, since I have a common factor of 8, that means I need to rewrite 6 in terms of 8. And the quickest way to rewrite 6 in terms of 8 is 8 minus 2. Which means now I can rewrite this as negative 2 plus 8 factored to give me the 1 plus x squared over 2 plus x cubed over 3 factorial plus dot dot dot. And now I have that plus 1. So I can now rewrite that in parentheses as e to the x because this forms my Maclaurin series for e to the x. Meaning my final answer will be negative 2 plus 8 e to the x power. And that gives me my final answer for that differential equation. That f of x has to equal 2 plus e to the x power. Now another cool thing that we can do with Taylor series is we can approximate a definite integral. And to kind of illustrate that with, I'm going to do that with e to the negative x squared. So I'm going to tell y'all right now that based off the tools that we have, I can't integrate this function. And that's because my antiderivative is not an elementary function, which means that is a function that we've typically become accustomed to play with. You will learn how to actually take this integral. And we'll learn that in 2060. Because the way that we're going to tackle that integral actually requires techniques from Calculus 3. But as of right now, I can still integrate by expressing it as a power series first and then integrating it term by term. Here's how we're going to do that. First, let's find the Maclaurin series for e to the negative x squared. So, before we tackle that problem, I want to recall the property of power series that I'm going to be using for this problem. If I have a function, h to the x, that can be rewritten as x to the m power, and I already know that f of x has the power series representation, which I'll just write generically, then it essentially tells me that I can now give a Taylor series power series representation of the composite of h of x and f of h of x and f of x by wherever I saw x originally, I replace with an h of x. And now let's do that for this problem. In this scenario, my f of x is e to the x, which I already know the Maclaurin series to be k equals 0 to infinity of x to the k power over k factorial. And in this case, the function I'm compositing is negative x squared, where b is negative 1, h is 2, which means my power series representation by this property from section 11.2 of the composition, which is e to the negative x squared, is going to be the sum going from 0 to infinity. And what that property is saying, wherever I saw x originally in my power series, I'm going to replace it with the function of h of x, which then gives me the following power series. After simplifying, k goes from 0 to infinity of negative 1 to the kth power, x to the 2k over k factorial. And there's our power series representation for e to the negative x squared. All right, and now with that, let's go ahead and figure out what the integral is as an infinite series. So now that I already know its power series, I can rewrite the inside of that integral as the power series representation that we found in part A. And now because I have a power series, integrating a power series, I'm going to use my property that tells me I can move the integral inside the summation and take the integral term by term. And the antiderivative of x to the 2k is 2k plus 1 over 2k plus 1. So I get, for my answer, the sum going from k equals 0 to infinity of negative 1 to the kth power x to the 2k plus 1 divided by 2k plus 1 times a k factorial, and then we have the plus c since I took an indefinite integral. Alright, and with that, let's use that information to evaluate the integral from 0 to 1 of e to the negative x squared, and let's try to be accurate and have that correct with an error of 0.0001 or 001. So, by step B, I could technically take the antiderivative of that and use fundamental theorem of calculus, because I'm just taking the integral from 0 to 1 of the power series that we developed in part A, which is that's 2k over k factorial. But from part B, I already know what its antiderivative is, so I'm going to use that fact now and rewrite this problem as the sum from k equals 0 to infinity of negative 1 to the kth power x to the 2k plus 1 divided by 2k plus 1 times k factorial, because we found that to be the antiderivative of the power series of e to the negative x squared. But because I took a definite integral, I still have to apply the fundamental theorem of calculus on that problem. Which, when I do that, I'm going to do the right endpoint minus the left endpoint. But my left endpoint, so I'm plugging in 0, and since this is just having x everywhere, I'm just going to get 0 regardless. So, with that, this now breaks down into the sum 0 to infinity of negative 1 to the kth power over 2k plus 1 over k factorial. So I found what the integral from 0 to 1 of e to the negative x squared is with respect to a power series. So now let's go ahead and try to answer that last bit of the problem. So, one thing I want y'all to note is this is an alternating series. And I'll go ahead and let y'all know that if I did check my criteria for alternating series test, it's going to pass both of them, therefore giving me that it converges by the power series test. By the alternating series test. So because of that, the way I could correct within an error is I could go back to section 10.6 and think about it from back then, which is I'm thinking about the remainder. Because remember what I kept saying throughout the course. Think of the remainder of a convergent series as the error of approximating that series with a partial sum. And because this is the alternating series, we can use our alternating series estimation theorem, which I'll write down below. which tells us that for the remainder of an alternating series, it is bounded by the next term over of the positive terms within that series, which, after calculating, will be 1 over 2. And because I'm plugging in n plus 1, wherever I saw a k originally, I'm plugging in an n plus 1. Oh, that should be purple. And now n plus 1 factorial. But I distribute the 2, I'll get 2n plus 2 plus a 1. I'll get 2n plus 3. So 2n plus 3, n plus 1 factorial. So I know what I need to estimate it. And I'm going to tell y'all right now that sadly for Yetz, based off of that guy, to give us a bound for 0.001, it's just going to be trial and error. And you could use whatever method you want to calculate that at your home. When I was making the notes, I wrote a MATLAB script to calculate the errors for if I want to estimate what the nth partial sum. So that's also a fair game that y'all can do as well. So, but when we do trial and error, we get that when n is less than, greater than or equal to 6, we are ensured that the error is going to be, or greater than or equal to 5, I'm sorry. The error is less than 0.001. And the reason why I say greater than or equal to 5 is, which means that when at the 6th partial sum, or the 6th term, I better get something less than 0.001, which means it will be at 5. If we add the partial sum that we have, we get that the sum of the first 5 terms is 0.747, meaning the following: that the integral from 0 to 1 of e to the minus x squared dx is approximately 0.747 with an error less than 0.001. And that's how we do that by approximating a definite integral. We essentially use our technique from before, do a power series, then bound it, and find the remainder of that power series. But now let's do something else and talk about how to represent a number as a form for a power series. So for this example, I want to find the exact value of that power series. And the main goal when it's saying to find the exact value of a power series, and not a power series because there's no x, of just a normal series, here's going to be our goal. Match, yes, with a known Maclaurin series. That's going to be our goal if we're asked to find the exact value of a series. We're going to try to match that with a Maclaurin series that we know, but the reason why there is no x here is because I plugged in a specific value for x, and we're going to figure out what specific value did we plug in. So for this example, I gave a hint that says consider the Maclaurin series for arctan in section 11.3 in the table at the end of the section. The Maclaurin series for arctan is k equals 0 to infinity of -1 to the kth power x to the 2k plus 1 divided by 2k plus 1. Now watch what happens when I plug in 1 into arctan. Now I said these are equal, which means no matter what value for x I plug in, they better be equal. So if I plug in 1 for arctan, that means I'll plug in 1 in within my power series. And if 1 raised to any power is just itself, and that gives us back the series that we want to find the exact value for. So now, to answer the question, find the exact value of the series, underlined below, it suffices for us to just know what is arctan evaluated at 1. And there's only one value that I know of, such that if I plug something into tangent, I get 1. And that's pi over 4. And so what I can conclude now, therefore, this sum from k equals 0 to infinity of -1 to the kth power divided by 2k plus 1 equals pi over 4 as my final answer. And so that's going to be our goal for these types of problems. If we're asked to find the exact value of a particular series, I'm going to try to match it with a Maclaurin series, and then from that match, I'm going to see if when I plug in something specific, I get the exact value that I want. And now, let's finish this up and express a function as a power series. And with this is going to be playing around with the property that we talked about before, which is if h is a function and f has a known power series, which in this case will be CFK and x to the k, then if I replace yes and make it a composition, then the corresponding power series is just plug in h of x. And now I only gave where h is b to the x of m, but as long as the function is continuous, we can still work with this. And so here's going to be our game plan. I see a 1 minus 2 of x in this power series. So that 1 minus 2 of x is going to act as my h of x for this problem. And now, if I replace that h of x with just an x, I get back just, there we go. I get back e to the x equals 2, just the normal Maclaurin series that we dealt with. Meaning, based off of that property, I get that series by just plugging in 1 minus 2 of x into our normal power series, or Maclaurin series. And there's my a function to represent the power series that I have. Well, let's now check if the interval of convergence still remains the same. Because recall that the original interval convergence for the Maclaurin series is infinity. So let's check if we still have that the interval is negative infinity to infinity. Well, the way we're going to start that off with is, because I know that I worked with the Maclaurin series for e to the x, and I know that the original interval for convergence is negative infinity to positive infinity, I'm going to work with that interval again, only this time I'm going to write that as 1 minus 2x instead of x, because that is what's taking place of x inside here, the function 1 minus 2x. If I subtract 1 from all sides, we get an inequality. I'll still have negative 2x in the middle of my inequality, but because I have minus and positive infinity, it's not going to change the order of that inequality. And if I divide everything by negative 2, I'll change the order of the inequality, but negative infinity times a negative number will just give me positive infinity. That's the negative infinity. So I still have that the interval of convergence is negative infinity and positive infinity. Alright, and that concludes this video. Later this week, I'm going to post a bonus video about, as you see in the title, Prepare for Your Minds to be Blown, where I'm going to show how we can use all the stuff that we've learned to prove a very cool identity called the Euler identity. But that concludes chapter 11. Hope to see y'all on the flip side.